Okay, greetings. Now this problem is based on a piecewise defined function as shown, and the question says to find the values of a, b, and c so that this function will satisfy the hypothesis of the mean value theorem. Now the mean value theorem in this problem here, the purpose of referring to the mean value theorem in this problem is not to actually use the mean value theorem, but really this problem is just trying to make sure that you understand the hypotheses or the conditions of the mean value theorem. Now the mean value theorem says that we need the function to be continuous on a closed interval and differentiable on the open, and those are the only conditions: continuous on the closed interval and differentiable on the open interval, and then there exists a c such that f prime of c is equal to f of b minus f of a or b minus a. None of that part really matters after that. We just need that we need to understand the conditions or the hypotheses so that we can meet that requirement for this problem. So what we need to show is that, or we need to find a, b, and c so that this function is going to be continuous at x equals negative 2 and at x equals 1, and then also differentiable at x equals negative 2 and x equals 1. And so there's those two things that we have to meet. Now, I'm not going to write out the solution in its entirety because in class I would require you to mention separately and write it out that each piece of this piecewise function is a polynomial, and polynomials are continuous on their domains and they're also differentiable on their domains. And so that each piece of this function, regardless of the values we find for a, b, and c, will be continuous and differentiable everywhere. So the concern right now for all other real numbers other than x equals negative 2 and other than x equals 1. So I would want that written out in a complete solution, but just for the purposes of this video, I'm only going to focus on the critical issue here for this problem, for this piecewise defined function, and that's at the values of x equals negative 2 and x equals 1, because this is where the piecewise definition changes, and we have to make sure that the transition from one definition to the next still has the function being continuous and differentiable at that point. So let's get into it. So the first condition that the function is continuous, we have to remember what the definition of continuity is. And so we have to make sure that we, show that the value of f of negative 2 exists, okay? And it does. If we go look at the piecewise defined function, the second piece has the or equal to sign, including the negative 2. And so that's, the function is defined by the expression 3x minus 1. And so this will be 3 times negative 2 minus 1, which is negative 7. So this function is defined at negative 2. The next part of the definition of continuity is that the limit exists at x equals negative 2, or as x approaches negative 2. And for that to be true, since the piecewise function changes definition at negative 2, we need the limit from the left to be equal to the limit from the right. So the limit as x approaches negative 2 from the left for f of x has to be equal to the limit as x approaches negative 2 from the right. Otherwise, the limit won't exist, and then the function will not be continuous at that point. The little plus sign next to the negative 2 looks a little funny there, but I'm not going to change it for now. All right, so the limit as x approaches negative 2 from the left, remember that means that the values of x are smaller than negative 2. And so if we go back to the definition, when the values of x are smaller than negative 2, the function is defined by that first piece, ax squared minus bx. And so I'm going to substitute in place of the name f, the actual expression defined there, ax squared minus bx. As x approaches negative 2 from the right, that means x is greater than negative 2. Now, there are two pieces in the definition for values of x greater than negative 2, but in the limiting process, we're looking for x to get closer and closer to negative 2. So we're not going to be concerned with the parabolic piece for x greater than 1. We're going to be concerned with the linear piece where the 3x minus 1 piece, because on that interval, x is greater than negative 2, and x can become arbitrarily close to negative 2 as well. So that piece is going to be the 3x minus 1. So for at this step here, we need to evaluate the left-hand limit and the right-hand limit. And since both of these are polynomials, we can use the direct substitution property, meaning I could just plug in -2 for x on both sides and then simplify the expression. I'm going to do some of this mentally because I'm almost out of screen space here. So if I plug in -2 and I square it, I get 4 times a gives me 4a. And then if I plug in -2 for x, so minus b times -2, which gives me a plus 2b on the left-hand side of this equation. When I plug in -2 on the right-hand side, I get that same -7 that we got for f of -2. So now, I need to find values for a and b, but I only have one equation at the moment, this one that's right here, and that's not sufficient for solving for a and b. I need more than one equation. I need two equations when I'm going to find two unknowns. So I need this relationship. Another relationship involving a and b. So we're going to repeat this process for what's happening at +1, the other place where the function changes definition. So we need to know that f of 1 exists. F of 1 is defined again by that middle piece because that's where the inclusive equal to sign is. So we'll get 3 times 1 minus 1, which of course is going to be 2, and that exists. I also need the left-hand and right-hand limits to be equal to each other. So the limit as x approaches 1 from the left of f of x needs to be equal to the limit as x approaches 1 from the right of f of x. And I'll go use the definitions again. I will substitute in the actual expression. Now, x is going to be less than 1, but x is also going to be approaching 1. So we'll use that middle definition, the 3x minus 1 piece. And so let's substitute that in place. And then the limit as x approaches 1 from the right is given by the last parabolic piece, which is cx squared plus 1/2. Again, we will evaluate these expressions here. So on the left-hand side, I'm going to get a positive 2. On the right-hand side, when I plug in 1 for x, I'm going to get c plus 1/2. And this is one equation with one unknown, so we can actually solve for c, and we can get 1.5 or 3/2 or whatever your favorite form is for writing it. So we're off to a good start here because we've already found the value of c that we're looking for. We just need to continue to find a and b. So I need another relationship, but remember, a condition that we have to verify here is that the function is differentiable at those values. Excuse me, I had to pause the video there for a moment, so I may be a little bit off in what I was disjointed from what I was saying prior to when I paused it. But nonetheless, I need to use the condition that we need the function to be differentiable as well in order to get another relationship involving a and b, so that I can solve for a and b. So we need to take the derivative of f, and we'll do it, piece by piece. And so I'm not going to refer back to the problem here, but that first piece was its derivative would be 2ax minus b, and this is for when x is less than -2. That little middle linear piece, the derivative will be just the slope of the line, so it's 3, and then that's when x is between -2 and 1. And then the last piece, we get 2cx as the derivative for x greater than 1. Now, to handle this last part, we're going to do it very similarly to what we did before. What we need to have happen here is we need the limit from the left of f prime to be equal to the limit from the right of f prime for this function to be differentiable to be differentiable at these transition points. And so we're going to take a look at the limit as x approaches -2 from the left for f prime of x, and we want to make that equal to the limit as x approaches -2 from the right of f prime of x. And from the left, we have the piece that was -2ax minus b. And then from the right, we have the limit, here's x approaching from the right. We had the piece, well, that was just the slope of the line, 3. So if I evaluate the left-hand side of this, letting x be negative 2, using direct substitution, we get negative 4a minus b is equal to, and then on the right-hand side, 3. So now we need to go back and grab that earlier equation relating a and b, 4a plus 2b equals negative 7, and solve the system. 4a plus 2b equals negative 7. The nice thing about this one is it already has it set up so that when we add these equations together, whoops, let me back that up, we get the a variable to cancel from each equation, and then we get a nice simple relationship, b equals to negative 4. I need to plug that back in, so to find a, so 4a plus 2 times negative 4 is going to be equal to negative 7. So 4a minus 8 is equal to negative 7. So that means 4a has to be equal to 1. And so a has to be equal to 1/4. Now we should go back and make sure that we have differentiability happening at x equals 1 for the value of c that we found. So if I take a look at the limit as x approaches 1 from the left for f prime, that has to be equal to the limit as x approaches 1 from the right of f prime. And so the limit as x approaches 1 from the left of f prime, well, that's that linear piece, that's 3 as our expression on that interval. And as x approaches 1 from the right, that is going to be the 2cx. And 3 will be how we evaluate the constant on the left, and then on the right hand side we just get 2c, and again we get c is equal to 3/2. So we do have differentiability at x equals 1 and continuity at x equals 1 when c is equal to 3/2. It might be a good idea, no, it is a good idea to go back and check plugging in the values of a, b, and c into the original function and its derivative, and making sure that these values do work by checking the definitions at all those transition points. It's just a good practice to do that because you may have, set it up logically correctly, but there may be a calculation error along the way. You want to make sure that that calculation error isn't actually there and giving you an incorrect answer. Go study.